I think this might be a slightly different approach than the one that you have seen previously. So let's see if I can, okay. Just to make clear, this is joint work with Professor Ruzba Hazrat, who I think is still logged into this. So thank you very much, Ruzba, for joining this morning. Well, this afternoon for some of you. And so here's an overview of what I'd like to do in the next 50 to 55 minutes. I want to share with you an idea that maybe some of you are already familiar with, that I usually refer to as Bergman's realization theorem. And then we'll look at, starting with the directed graph, a natural class of monoids that arise from the graphs. And then I'll talk about this essentially independent idea called Sandpile models. And then in section 4, the connection between these ideas, and then what we might think about as next steps in the development of this perhaps new theory. So I'll start very basically. If you take a field and you consider the vector spaces that just look like direct sums of copies of the field, then this is a standard undergraduate linear algebra exercise to show that these vector spaces can't be isomorphic one to the other. There's some notion of basis and dimension in vector spaces over fields. And the same is true if you take direct sums of copies of the integers and you view these as abelian groups, then it's not hard to show. It's a little bit more work than in the vector space case, but it's not hard to show that these are also non-isomorphic pairwise as abelian groups. Okay, so a natural question becomes, all right, if I change the ring instead of a field or the integers, does the same sort of property hold? That is, if you take direct sums of copies of the ring, is it necessarily the case that a different direct sum of a different number of copies is necessarily different? And the answer turns out to be not necessarily. And this was the beautiful insight that Bill Leavitt had now 60 years ago, more than 60 years ago. And the idea is what Bill Leavitt was able to show is that if you give me two integers m and n, two positive integers m and n, that you could write down a ring with the property that the free modules r direct r, etc., up through r direct sum with itself n-1 times, that collection of modules over r are all non-isomorphic one to the other, but then the nth term is isomorphic to whichever choice of m you've chosen less than n. So you can build rings that have the property that there are some non-trivial isomorphisms between the direct sum of two different numbers of copies of the ring. And it's not that these are just esoterically out there somehow. Bill Leavitt was able to explicitly write down what these algebras look like. It turns out, well, in retrospect, I think we're understanding this a little bit better over time, but the algebras corresponding to R1 isomorphic to some direct sum of copies of more than one copy of the ring. So what we call the L1n algebras turn out to be significantly different structurally than the algebras that look like LMN for m bigger than or equal to 2. And I'll talk about a little bit about what some of those structural differences are. And in the end, you can think of Leavitt's theorem as, okay, anything that can happen does happen. And the question is, okay, I mean, in the day, I think it's fair to say that the ring theory community looked at Leavitt's theorem and said, okay, you've built these algebras, now we're convinced they exist, but why are we interested in these? What more might we be able to say about them? Okay. So here also is some background that for most of you will be just a review. Throughout, rings are associative and unital. I'll work with left modules. You can work with right modules if you choose. K will always be a field. Finally generated projective module is simply a left R module with the property that you can form its direct sum with some other left R module and get some direct sum of copies of the ring. So of course, any module, any direct sum of copies of the ring is finitely generated projective. We call such modules free modules. There are many examples of finitely generated projective modules that are not free modules. For example, if you pick a non-trivial idempotent in a relatively nice ring, then it's always the case that RE will be finitely generated projective, but not necessarily free. Let's see. And the point is, right, exactly this, that if you look at a finitely generated projective, your model of what these should look like are free modules. But in this nice, straightforward situation, if the ring is just the 2x2 matrices and you look at the first column, then you get precisely a module of this form, R times E. And it's interesting to note, and we'll sort of make use of this later, that I mean, what I've looked at here is the first column of the 2x2 matrices. If you look at the second column of the 2x2 matrices, you obviously get a different module, but those are isomorphic as modules over R. All right, so I know many of you are interested in semigroups and monoids. This is where things I think will become interesting for you. If you take any ring, you consider the isomorphism classes of these finitely generated projective modules over R, you get a commutative monoid. The operation is simply direct sum. The neutral element, which I'm going to hesitate to call the identity element. So the neutral element, the element that you add to anything, turns out to be just the zero module. Okay, now let's look at trying to compute explicitly what this V monoid is for any given ring. For instance, if you start with just the field, okay, well, we know what the finitely generated projective modules are there. Well, every finitely generated module over a field has a basis is free. And so the finitely generated projective modules over a field are in one-to-one correspondence with the integers, the non-negative integers under addition. Okay, so that's an easy one to look at. You have to work a little bit harder, but not much harder, to show that if you take this ring that we call the ring of Laurent polynomials over a field, so polynomials in either X or X inverse, that the finitely generated projective modules also just look like the non-negative integers. We, in a little bit, will look at more examples, but keep in mind, if someone simply hands you a unital ring and says, and ask the question, what is the V monoid of this ring? That's usually a very hard question. Okay, now in general, this V monoid has a property that we call the conicality property, where we say that the monoid is conical, meaning if you take the sum of two things in the monoid and you get the neutral element, that can only happen if each of the pieces is zero. What we also have in these monoids are what are often referred to as distinguished elements, namely, you find this special element in the monoid, and this special element has the property that as long as you look at enough sums of copies of itself, eventually you can dominate any other element in the monoid. And this distinguished element, I mean, typically there could be many of them. There's no notion of uniqueness of this distinguished element. But in the context of this V monoid of a finitely generated projective modules, obviously the ring itself works essentially by definition, but of course then any direct sum of copies of the ring would work as well. Okay, just as an example of distinguished elements in sort of familiar monoids, these are straightforward to write down. Okay, this particular monoid will play an important role here. I'll denote it by C sub n. So take any positive integer, look at the monoid consisting of 0, some symbol called x, x plus x, etc., through n-1 copies of x, and then you deem that n copies of x is the same as x. Not the same as 0, but the same as x. So this is easily shown to be a finitely generated commutative conical monoid, distinguished element x, or essentially any non-zero element in there. More generally, and I'll denote these monoids by C sub mn, you look at the same set, but then you put the relation nx is mx. And again, you get this more general notion of a finitely generated commutative conical monoid with a distinguished element, and in the notation, C1n will just be the Cn monoid. Okay, now one thing to keep in mind, you're thinking, well, monoids are usually just generalizations of a group. So abelian monoid is a generalization of a abelian group, but don't think in those terms here, because this conicality property means that if you think of groups, you're not going to get something conical because everything can sum to 0. So you're thinking typically the positive integers. That's a good example to keep on, or the non-negative integers. Okay, here's Bergman's realization theorem. This is George Bergman. This appeared in the Transactions in the mid-70s. And the question then becomes this: if you give me some commutative monoid, can you realize that monoid as the V monoid of some associative unital algebra? So that's the realization part. Okay, well, there's some minimal conditions. You need conicality, for example. You need the existence of a distinguished element. But what Bergman was able to prove is essentially that's all you need. If you give me any finitely generated commutative conical monoid and you point to a distinguished element, then what Bergman gives is a recipe, a constructive recipe to build a ring. And in this talk, I'll call the ring capital B for Bergman. And the recipe that you need to, the ingredients that you need to create this recipe are the monoid, but more than just the monoid. You need to describe the monoid as some quotient of a finite direct sum of copies of the non-negative integers modulo some collection of relations. And then you need to determine which element in there you're going to distinguish. And then what Bergman did was says, here's how you build an algebra for which the V monoid of that algebra with operation direct sum is precisely the monoid that you built. And in this construction, the algebra corresponds exactly to the distinguished element that you've chosen. It's a beautiful result. It's the word I like to use is delicate. He formally constructs this algebra, this B algebra, but delicate. And here's what I mean by delicate. It seems like I asked you to hand me a lot of information. You have to hand me not only the monoid, but how many copies of the non-negative integers you've used, what the relations are that you've used to build the monoid, et cetera, et cetera. And so here's a good example to keep in mind. So if I just look at the monoid of non-negative integers, okay, non-negative integers is, well, it's already one copy of itself, and there's no relations. And okay, pick a distinguished element. Let's pick one. There's a lot of choices. Of course, I could pick any non-zero element. Then with the Bergman recipe and these ingredients, precisely the Bergman algebra is just the field. Okay, you'd expect that. Of course, it has the correct V monoid. But now I'm going to give you the exact same monoid. Okay, so T is 1. There's one copy of it. But now I'm going to ask you to put a relation on this monoid. And the relation is 1 equals 1. And you're thinking, well, that's no relation at all. But it's a relation. I'm asking you simply to write down 1 equals 1. Then the point is, if you hand to the Bergman process this monoid with this relation, then the ring changes. The algebra that the Bergman process constructs is not just the field, but it's KXX inverse. Somehow into the computation of the algebra, this relation that 1 equals 1, even though it's a trivial relation, turns out to be encoded in the algebraic structure of the Bergman algebra. Okay, this is what I mean by delicate. Okay, and also if you change the distinguished element, you'll get a different algebra. For example, if we, in this first construction, instead of the distinguished element being 1, we choose it to be 2, then the corresponding Bergman algebra will be the 2x2 matrices. Is there a question? No? Okay. So what has happened over time is, I mean, it becomes very cumbersome to say, here's the monoid, and here's the number of copies of the integers, and here's the relations, and here's the distinguished element. We simply often, but this is really imprecise, we write B sub m, where m is just the monoid. Okay. So here's a monoid, this C sub n monoid. So T is 1, the relation is nx equals x. We can pick a distinguished element, let's say it's x. And the question is, what's the Bergman K algebra for this data? And the answer will turn out to be the Leavitt algebra. And here's how that works out. The Bergman recipe produces, when you look at all of the details, 2n elements. It produces the algebra in 2n non-commuting indeterminates. The relations are given as I've listed here on the screen. There's one set of relations that correspond to how you multiply the x's times the y's, another set as to how the y's times the x's interact. And it turns out that this algebra is precisely the Leavitt algebra LK1n. So the Leavitt algebras LK1n are Bergman algebras. And why should this be the case? Okay, well, at least you can show that R is isomorphic to Rn. That's straightforward to do. In this case, I've called it A. A is isomorphic to An as left A modules, because the elements that this Bergman recipe produces gives you a way of getting from A to An and back that turns out to be invertible. Okay, a couple of comments. One is, so what Bill Leavitt did not show in his paper, but turned out to be true and was only sort of realized once the Bergman theorem was proved in the mid-70s, is that this collection of A through An minus 1, not only are all the finitely generated free modules, they're all the finitely generated projective modules. And what Leavitt was able to show, and this was really the hard work in this article that he wrote, is that, okay, you have these left A modules, A squared, et cetera, up through An minus 1. How do you know that somehow there's not some unintended isomorphism between those? And it turns out that there is not. Okay, and it turns out that at least in this context, there was nothing special about m equals 1. That if you hand to the Bergman machinery these monoids C sub mn and you ask what's the corresponding Bergman algebra, the answer is you get precisely the algebras that Leavitt built in his 1960 paper. Okay, that's section 1. So section 2 is, how do we associate with directed graphs certain monoids? Right, and so this is, I know, is a very busy slide, but the idea is you start with the directed graph and you want to somehow build from it a monoid. And well, it turns out there are many ways to do that. For us, the interesting way to do that is this. You take for us today, just a finite graph with finitely many vertices, finitely many directed edges. You form a monoid. The monoid is the direct sum of copies of the non-negative integers taken however many vertices there are in the graph. So you have all these vectors with non-negative integer entries indexed by the vertices. And then what you do is you look at the elements of z bigger than or equal to 0 indexed that way. You look at the standard basis vectors corresponding to each of the vertices. And then you impose a relation. And the relations are going to be imposed by look at each vertex, see which the edges are that emit from that vertex, and then define a relation that says this vertex is the same as whatever the sum of the images are of the edges that that vertex points to. So that's a lot of words. I'll give you a specific concrete example to help make things a little bit clearer. But what we call the corresponding monoid is the graph monoid of E. And it's straightforward to show that this is finitely generated, commutative, conical. And okay, there's lots of distinguished elements that we could pick. We usually pick the one that just looks like the one corresponding to a 1 in each of the slots. Okay, so as promised, here's an example. So here's a graph that has 3 vertices. So I'm going to build a direct sum of copies of 3 copies of the non-negative integers, and then I'm going to mod out by a set of relations. And the relations are, well, you see from vertex 1, there's exactly 1 arrow being emitted. So vertex 1 to vertex 2. And so I'm going to set in my relations vertex 1 equals vertex 2. The vector corresponding to vertex 1 equals the vector corresponding to vertex 2. Similarly, from vertex 2, there are 3 edges being emitted, 1 to vertex 1, 1 to vertex 2 itself, a loop at 2, and then an edge from vertex 2 to vertex 3. So in the relations, we deem that the vector corresponding to vertex 2 is the sum of the vertices corresponding to vertices 1, 2, and 3, okay, etc. And so for those of you that maybe are, well, just interested in sort of scribbling some computations, what you can show, it's sort of interesting, is that if you look at this monoid, so z direct sum z plus direct sum z plus direct sum z plus modulo these relations, in theory, this could be finite, could be infinite, could be anything, but it turns out you just get a monoid with 4 elements, the monoid C sub 4. So I'll let you work on that as homework or during this talk if you prefer. Okay, so now this may come as a little bit of news for those of you that have seen Leavitt path algebras before. Here's the definition of a Leavitt path algebra of a graph. You start with, okay, in our case, a finite graph. You build the monoid that we just defined, the monoid corresponding to the directed graph. So I've specified how many copies of the non-negative integers to take. I've specified exactly what the relations are. I've specified what the distinguished element should be. And now what I want you to build is precisely the Bergman algebra corresponding to that collection of inputs into this recipe. And by definition, that's the Leavitt path algebra of a graph. So for those of you that are expecting, well, if he's going to give the definition of a Leavitt path algebra graph, I'm going to see all these things called CK1 and CK2 and V and E, blah, blah. Okay, I could write those down. But in effect, and most importantly, I think for today's talk, you should think the Leavitt path algebra of a graph is nothing more than the Bergman algebra that's produced by starting with this data. The data that gets produced by the directed graph when you look at the corresponding relations on the edges. Okay, so in theory, I mean, the Bergman algebra construction is explicit. So the Leavitt path algebras can be explicitly constructed. And again, many of you probably know how to do that, but that's not of interest today. But the punchline is immediately from Bergman's theorem, we get that the V monoid of the Leavitt path algebra is precisely this graph monoid. This comes for, I won't say for free because you have to work hard to get the Bergman theorem, but okay. A few examples. So if I just start with a graph with a single vertex, then here's the graph monoid. Okay, we've seen this before, so we know who the Leavitt path algebra of this is because it's the Bergman algebra of this particular monoid. And we've already seen what that is. And similarly, if you start with a graph with 1 vertex and 1 loop, then we know what the corresponding Bergman algebra of that is. And we know what the corresponding Bergman algebra of this second monoid or this third monoid is as well. So sort of, I won't say easily, but we get this sort of nice relationship between the graphs and the algebras through Bergman's realization theorem. Okay, and so here's the sort of, you know, famous example. Now I start with a graph with 1 vertex and n loops at that vertex. So, okay, I know exactly who the graph monoid is. There's 1 copy of the integers. There's a relation. It's 1 relation that says this vertex equals the sum of the vertices to which all the edges point. All the edges point back to that same vertex. There's n edges. And so the corresponding Bergman algebra for this graph monoid is nothing more than the Leavitt algebras. Okay, so just to sort of stop for a minute. So if we start with this Cn monoid, so the monoid 0x up through n minus 1x, but then we deem nx to equal x, then we can write down a graph and its corresponding graph monoid is C sub n. And so then we can build the corresponding Bergman algebra and thereby get the Leavitt algebras. The question is, if we start with these other monoids, these C sub mn monoids where m is bigger than 1, can we find a directed graph whose graph monoid is isomorphic to these more general Leavitt monoids? And the answer turns out to be no. So as I mentioned previously, there's this sort of dichotomy between what happens when when m is 1 and when m is bigger than 1. And here's the dichotomy. I won't spend too much time here, but I know there's some experts in semigroups and monoids here. It turns out that, and this is an absolutely, this to me is one of the 2 key papers I think that really got the ball of Leavitt path algebras rolling at the beginning, is this paper by Moreno and Pardo. And what they were able to show is that this graph monoid has what's called the refinement property. And if you've heard of that, great. Otherwise, it's not so important to know exactly what that means. But the point is, any one of these graph monoids has this property that if you take an element of the monoid and you write it as a sum of elements from the monoid in 2 different ways, then somehow that decomposition really has something to do with each other, that you can't sort of independently decompose an element. But it turns out in these CMN monoids where m is bigger than or equal to 2, these monoids do not have this refinement property. And it's easy to see that these monoids for m bigger than or equal to 2 do not have the refinement property. Moreno and Pardo had to work hard to show that the monoids m sub e do, but that at least says that we can't realize the CMN monoids as simply coming from a directed graph in the usual way by writing down the usual definition of a graph monoid. Okay, so here's what we do. We expand the collection of monoids coming from a directed graph so that this expanded collection will include these at least CMN monoids, if not more monoids as well. And this, my co-author, Hazrat, was sort of the founder of this idea. This notion of weighted graph monoids, you hand me a directed graph. Okay, there are a lot of ways of associating a weight with the pieces, with the ingredients of the graph. For today, all we'll do is we'll talk about some notion of, you take a directed graph and at each vertex you assign some positive integer. We call the weight of the graph. Formally, you don't need to assign a number at a vertex that's a sink in the graph. Okay, so you talk about the weight of a vertex. And then what we're going to do is expand the notion of what a graph monoid is to this situation of weighted directed graphs. And the generating set is the same. It's, you just take a direct sum of copies of the non-negative integers corresponding to each of the vertices. But now the relation that you impose incorporates the weight at each of the vertices. So the relations that you're imposing is the weight of the ith vertex times the ith vertex is then set to exactly what the same relation piece of that relation was in the non-weighted case. So we get this quite natural collection of monoids. It's a more extensive class of monoids than just the graph monoids were. But we again get finitely generated commutative conical monoids with, well, lots of distinguished elements. Okay, well, look, here's sort of the trivial way of putting a weighting on a directed graph. Just assign the number 1 to each of the vertices. Sure. And then what you'll get if you build this more general model in that specific case is just the usual notion of a graph monoid. So we get nothing new if we assign the integer 1 to each of the vertices. But more interestingly, for example, if I start with this rows with n petals, this graph that has 1 vertex and n loops, and we assign the weight m to the vertex, then here's what the corresponding weighted graph monoid looks like. So there's one relation, and the relation is whatever the weight of the vertex is, and we've assigned it weight m, should be the sum of each of the edges. And so what we get is precisely this more general monoid C sub mn. Okay. So in the notion of weighted graph monoids, we capture the CMN monoids that we looked at previously. A quick remark here, in this specific situation, there's some symmetry, meaning if you were to start with the graph with M loops and assign to the vertex the weight N, then, okay, then you're setting N times 1 equal to the sum of M copies of the vertex, and you get again CMN. This sort of symmetry happens here, but won't happen too often, but it's worth making note of at this point. Okay, so hopefully you can anticipate what the definition is going to be. You start with a vertex weighted graph, so a directed graph at which you've assigned a non-negative or positive weight to each of the vertices. Now we have this way of producing a finitely generated commutative conical monoid with a distinguished element. So you do that, and then you simply build the Bergman algebra corresponding to that data. That by definition is the weighted Leavitt path algebra. Okay, by definition, well, not really. The original definition as given by Hazrat was this list of generators and relations, but in the end, that's precisely the description of what you get if you build the Bergman algebra corresponding to the monoid with this data. So again, there won't be any definitions of these Leavitt path algebras or weighted Leavitt path algebras in terms of generators and relations. It's simply, here is what this thing is. It's the Bergman algebra corresponding to a monoid. Okay, and again, just as with the Leavitt path algebras, we can explicitly construct these, but we won't do it today. And the point is we have perfect information about what the V monoid of this algebra is. It's precisely the weighted graph monoid that we started with. Okay, but look, what we've done by expanding the collection of monoids that we looked at is thereby also expanded the collection of algebras that we're considering, these weighted Leavitt path algebras. So the point is that the weighted Leavitt path algebra, for example, for this weighting omega m on the specific graph that we just looked at, those can't be Leavitt path algebras because the corresponding V monoids don't have the refinement property. And the Ara-Moreno-Pardo theorem says that if you're looking at a Leavitt path algebra, think the Bergman algebra corresponding to a standard graph monoid that has to have the refinement property. So that's an easy way using this very nice result to show that we really are getting an additional class of algebras here. Okay, now I get to tell you about what to me was a new idea less than a year ago. I had never seen these before, but I think the idea is really intriguing, and I think that many of you will find it interesting. Okay, this is the notion of a Sandpile model. Okay, so this is just different than what I've talked about for the last half hour or so. So there are some real world systems that many of physicists, applied mathematicians have considered that can be partially understood by looking at models that I'm about to describe for you. I'm certainly not going to give you the formal definition of what these models are, but I'm going to show you enough examples, I hope, to give you some flavor of what these look like. So this is sort of the one way of thinking about this. Consider a square grid. Think of the screen on a door or something like that. So each node in this grid has 4 neighbors. Okay, the ones on the boundary, maybe not, but we'll deal with those a little bit more specially. And here's how we're going to disperse some objects on this grid. View each of the nodes in the grid as having something piled at it. Sand, grains of sand, or poker chips if you like to play poker, something like that. And the way things will be dispersed is if you have 4 or more things sitting in a specific node, you disperse those things to each of the neighbors. Okay. So for example, just to run through a quick example, I won't spend too much time on this. So suppose I have this 3 by 3 grid. So I have 9 nodes. I've listed numbers here that indicate how many grains of sand I've piled at each of the nodes. And here's how the dispersion process works. So there's the original configuration. Let's see, if I disperse at that center node, then what had been 9 grains becomes 5 grains because I disperse 1 grain to each of the 4 neighbors. So you'll see at each of the 4 neighbors, the number has increased by 1. I can then disperse maybe at the left-hand middle node. So there had been 6, I shoot 1 to the top, I shoot 1 to the bottom, I shoot 1 to the side, and then the 4th one just sort of falls off and disappears. Okay, that's the understanding of what happens at the border. Okay, here's a process. For example, you can ask, if I were to continue this process, would I eventually get to some configuration where I can't do any more dispersion? And if so, if you and your friend started with the same configuration and you both got to some configuration where you couldn't disperse anymore, would you be looking at the same configuration? And the answer turns out to be yes. So there's some interesting sort of stability processes here, uniqueness of the stability process. Okay, I'm going to spend 1 minute to show you this. I find this incredibly fascinating. Here's an example. What if you take 1,640 grid by 1,640? It turns out, and we'll see an example of this, I think I'll have time to do this. It turns out within this operation of dispersion, you get to these stable states. You can talk about adding stable states together. We'll see that in a minute. You might not get a stable state, but then we'll just ask you to stabilize that out. Among the stable states, some subset actually forms a group. We'll see that in a little bit. And so you can ask the question, what does the stable state corresponding to the identity element of that group look like? Okay, well, stable states have to have either 0 grains or 1 grain or 2 grains or 3 grains of sand, because if you had more than 3 grains of sand, then it would disperse, it wouldn't be stable. Here's what the identity element looks like. And if you're interested to see some really wonderful, I don't know, both computer programming point of view as well as mathematical, I don't know, insight, go on YouTube and search for Sandpile's number file. You'll get a really nice description of how these fractal looking objects come up in the notion of these Sandpile models. Okay, so I'm not going to talk about this picture again. I just want to sort of whet your appetite as to how this subject might be incredibly interesting, both from a physics point of view as well as a mathematical point of view. Okay, so here's more generally the type of Sandpile models that we're going to be interested in this context. So instead of just having this grid where there's no sense of direction to the edges, now think of a directed graph, and we'll impose this Sandpile dispersion idea on the directed graph. So the idea is at each vertex in the directed graph, you can pile grains of sand or poker chips or whatever it is again. And the model will have this dispersion process where if you're standing at a vertex, you count the number of edges that come out of that vertex, so directed edges now that come out of the vertex. And what you do is, if at that vertex you've piled at least that many grains of sand, then you simply disperse those along the edges that leave from the given vertex. So it's the sort of natural directed generalization of the model that we just looked at on a grid. And I've listed out more formally what the algorithm is here, but the intuition is simply you start with a graph, you have this way of dispersing objects that might be piled at each of the vertices, and that way of dispersing simply depends on how many edges are coming out from each of those pieces. Okay. Right. So you can do that in general. But we're going to do that in one very special context. And the special context is you assume that this underlying grid is what we've been talking about, looks like some finite directed graph. But you assume a little bit more. You assume there's a unique sink in the graph. So there's exactly one vertex that emits no edges. And you assume that each vertex in the graph has the property that there's a path from it to the sink. And then finally, you assume that any grain of sand that arrives at the sink just disappears. Okay. So we'll call such a graph a directed Sandpile graph, and we'll call this model, this dispersion model of things that live at the vertices in such a graph, a directed Sandpile model with elimination. Okay, that's a word, but that's the intuition that things are somehow moving in the graph in a specified way, and that specified way depends on the out degree of the given vertices and the fact that you've got a unique sink to which everything can lead. Okay, so question, do we have the same notion of stability? Do we have the same notion of uniqueness of stable representation? We get that. Okay, so now here's what we do. If you hand me one of these directed Sandpile graphs, you can ask about which of the configurations, in other words, which of the ways of piling things at each of the vertices is stable, has the property that there's no dispersion that can happen. Okay, well, that happens precisely when the number of grains of sand that you've listed at each of the vertices is less than the out degree of each of the vertices. So how many stable configurations are there? Well, you have at each vertex, you tell me what the out degree of the vertex is, n, let's say. So you have exactly n configurations that are stable. Either you have no grains of sand or 1 grain of sand up through n minus 1 grains of sand. So you can determine how many stable configurations there are in this graph. You just take the product of the out degrees of each of the vertices. The sink is special. We're not gonna, I mean, we've thrown away things that go to the sink, so we don't have to worry about the sink. So those are the players in this monoid that we're about to create. And now we're gonna look at an operation on this set. And the operation is, I'll denote it by direct sum. You take 2 of these stable configurations and you simply add the number of grains of sand together at each vertex. I mean, it's sort of the logical thing to do. The problem is when you do that, the configuration that you get might not be stable. Okay, so what you then do is you take this configuration that might not be stable and simply run this process, do the dispersion process until you get the stable configuration that you wind up getting to. That we define as to be the sum of these 2 configurations, stable configurations. Okay, and you get a finitely generated commutative monoid. Heck, you get a finite monoid. We know what the size is. We just computed the size of the monoid. And the 0 element is exactly what you'd expect. You put 0 grains of sand at each of the vertices. There are plenty of distinguished elements in here. So what's the piece that's missing in order to get to all the stuff that we've talked about for the last 45 minutes? What about this conical property? Yeah, maybe not. Okay, so it's a little bit surprising. I mean, there's an easy example. If you give me this directed Sandpile graph, then here is a stable configuration. Just put 1 grain of sand at the one vertex that's not the sink. So that's stable. But look, if you add it to itself, you get 2 grains of sand at that vertex. But now you have 2 grains of sand. So the dispersion process happens because the out degree of that vertex is 2. And both of the grains of sand go to the sink and then disappear. And so the corresponding sum of this element with itself is 0. So the monoid in general is not conical. Okay, a few words. This first one is not standard, I don't think. We call a vertex irrelevant if it only emits one edge. Okay, well, it's not irrelevant in general, but in the context of these monoids, they will be precisely the ones that we're not interested in. Okay, a cycle is just a way of getting around in a directed graph. It starts and ends at a vertex that doesn't revisit the vertex. And we say a vertex connects to a cycle if you can draw a path from the vertex to the corresponding cycle. Okay, here's the theorem. The people that work in these Sandpile monoids, I don't think use the word conicality or conical here, but it turns out they've already proved the theorem. They know when the Sandpile monoid is conical. It's precisely when every non-sync vertex that doesn't connect to a cycle is one of these vertices that has out degree 1. So fine, maybe it's the case that when we look at these Sandpile monoids, we don't always get a conical monoid, but we often do. And it's easy to figure out when we do because they'd already proved the theorem. Okay, so here's the big connections, right? So here is a directed Sandpile graph. You take one vertex that has some loops at it, you take another vertex that's going to act as the unique sink. Tell me how many loops you have at the vertex. Tell me how many edges you've pointed to the sink. Okay, I've given you some numbers to indicate those things. So here is the directed graph. And so it's a Sandpile graph, so we can form the Sandpile monoid. And here's an element of the Sandpile monoid. Just put one grain of sand at this non-sink vertex, and then just start adding that configuration to itself. Well, add it to itself. You get 2 at that vertex and 3 at that vertex, etc. And at what point is it the case that the corresponding sum of this element with itself becomes unstable? It's when you have as many grains of sand there as the out degree, but the out degree is precisely n+k. I have n loops at it plus k edges going to the sink. And when this dispersion occurs, what's left? Well, k of the grains of sand have gone to the sink and disappear, and n of those grains of sand have gone back to the given vertex. So here is the relation in the Sandpile monoid. In other words, we get precisely these C sub n, what I had called C sub mn graphs before. Okay, we're going to want to change the notation for a reason, just to show how these things connect up with the Sandpile monoids. And so here's the connection. And the idea is, okay, we've sort of seen the connection now. You start with some directed Sandpile graph. You form the Sandpile monoid. We know how big it is. It's finally generated. It's commutative. It's got as many distinguished elements as you'd like. It might not be conical. Okay, too bad. But we can sort of figure out how to mod out the I don't know what the word is, conicality or conicalness from the monoid. You identify a special subset of the graph. It's the collection of vertices that don't connect to a cycle. Okay, you throw the sink in there too, obviously. So for those of you that know the words, I'm not going to spend any more time on this. So these words come up quite often in the context of Leavitt path algebras. What we've got inside this graph is a hereditary saturated subset. Okay, we're not going to really need that idea here, but here's what you do. You form the graph where you remove these vertices, you remove all of the edges that hook to these vertices, you view the corresponding graph that's left over as a subgraph, you weight the elements of the subgraph just by taking the restriction of the weighting on the original graph. And then there's one more piece, and then we get to the connection. And the one more piece is, remember we talked about this notion of weighting on the vertices of a graph. There's a very natural way of weighting the vertices in a graph. I mean, by definition, I can put any positive integer I want at each of the vertices and build this monoid. The way I'm going to ask you to do that is take the directed graph that you've been handed, assign to each vertex a weight that's equal to its out degree. So simply tell me how many edges leave that vertex, and that's the weight that I want you to assign to that vertex. We'll call that the balanced weighting. I don't know, we just made up a name for it. So it's one of these weighted directed graphs now. For example, if I start with this G n+k, n graph, the weighting now that I'm going to assign to the vertex V is n+k because that's its out degree. And then here's the theorem. You start with a conical Sandpile graph, and we know exactly which those are. You take this balanced weighting. So here's the weighting. You identify the weighting by simply assigning to each vertex its out degree. You throw out the vertices that we don't really want. You throw out the set S. So then you get a subgraph. And in the end, you can then realize the Sandpile monoid as the monoid of the weighted graph that you get by looking at what we've called G mod S and the restriction of beta. In particular, the Sandpile monoid is precisely the V monoid of the weighted Leavitt path algebra corresponding to this data. So we can build an algebra it turns out to be an algebra that we've already studied, these more general Leavitt path algebras, these weighted Leavitt path algebras. We can explicitly build an algebra whose V monoid is the Sandpile monoid. Okay, it's nice. Oh, right. I mean, I've sort of given you the flavor of how this should work. Okay, but I'm not going to prove the generalism, but I mean, we've seen the specific example, right? Here is the sort of canonical example. You start with this particular Sandpile graph, you build the Sandpile monoid, you put the appropriate weighting on it. Let's see, what are we supposed to do? We're supposed to throw out any vertices that don't connect to a cycle. Well, the sink certainly doesn't, but everything else certainly does. So we throw out the sink. And what's left over are just the loops. But the weighting remains. It's the restriction of the weighting on the original graph. It's N+k. And so we get that this monoid is precisely. Okay, that's the idea here. Yeah, and it turns out there's a way of starting with a non-conical graph and getting a similar type of result. It's just you have to take the Sandpile monoid and mod out by some appropriate submonoid. And I don't want to spend any time talking about that today, but there's more to it. We can sort of incorporate what happens when the graph is not, I'm sorry, when the corresponding monoid is not conical. Okay, so last 5 minutes, what's left? What have we done? Right, so let me try to give you sort of the big view of where a lot of these pieces fit. Right, so we have this collection of monoids that arise as the V monoid of some associative unital ring. They are, by Bergman's theorem, the finitely generated commutative conical monoids. Okay. All right, some of these monoids are isomorphic to the vertex weighted monoids. Some of them are isomorphic to the standard graph monoids. And some of them are isomorphic to both a standard graph monoid and one of these weighted, one of these Sandpile monoids. Okay, so we know what U is. Here's what we've shown today, that the collection of monoids that arise both as a conical monoid and a Sandpile monoid, well, live inside the collection of monoids that arise as one of these weighted graph monoids. And it turns out, I guess intuitively, there aren't very many monoids that are both a Sandpile monoid and a refinement monoid. Right, I mean, the standard Leavitt monoids L1n, so the C sub 1n monoids are, and sort of trivially direct sums of those will be, but it turns out that's all of them. And so as far as how things sort of piece together, here's a diagram of the monoids that we've looked at. Okay, so what's the, I don't know, what's the appropriate follow-up question? Well, now we can talk about the notion, I guess, of a Sandpile algebra. You start with a conical Sandpile monoid and you build the Bergman algebra from it. So we'll call that a Sandpile monoid. I'm sorry, a Sandpile algebra. You start with the Sandpile monoid and you build a corresponding algebra. So what do these algebras look like? Well, at least these algebras contain not only the L1n algebras, the sort of standard Leavitt algebras, they contain all of the algebras that Leavitt built 60 years ago now. They contain all of the LMNs for any value of M. Which is nice because remember, the standard Leavitt path algebras don't contain the LMNs for M bigger than or equal to 2. So at least for us, the intuition is now we've written down a class of algebras, these Sandpile algebras, that simultaneously contain all of the Leavitt algebras, all of them, independent of the value of M, but don't necessarily contain the entire universe of weighted Leavitt path algebras, which seems sort of I don't know, too big if your goal is to try to figure out some structural properties of these Leavitt algebras. Okay, so what are the appropriate distinguished elements to pick? Well, I mean, there's sort of a natural distinguished element. Just put one grain of sand at each of the appropriate vertices, but you know, we can pick any other choice. And in this context, unlike the standard contexts, there's sort of another natural choice for a distinguished element, which is put the maximum number of grains of sand at each vertex so that the corresponding configuration is still stable. Okay, we can do that, but at least for now, we'll just focus on the one, and here then is the corresponding diagram that represents what the algebras look like. Okay, yeah, I'll take the last 2 minutes here maybe to sort of obliquely mention an interesting question that's still out there in Leavitt path algebras. So remember, the point is, just because you give me the same monoid, if you represent it differently, the corresponding Leavitt path algebras might be different. And we've already seen examples of that. Oops. Right. But now the question is, what if the monoid that you've given me is one of these C sub n monoids? So remember the examples that we looked at before where things turned out to be delicately strange, the monoid there was z bigger than or equal to 0. If you hand me one of these Cn monoids, the question is, does it matter how you've represented it in the context of building the corresponding Bergman algebra? So the question is, if I hand you one of these Leavitt path algebras and its V monoid is C sub n, and okay, I'm going to require that the corresponding distinguished element be 1, is it necessarily the case that the Leavitt path algebra looks like LK1n? And it turns out the answer to this question is not known in general. And Rusba Hazrat's going to give a talk later in this conference that describes really in more depth how this question plays out. But this question seems to touch a lot of the aspects of Leavitt path algebra theory. Okay, so this is too big of a graph to deal with, but here is, in my opinion, the most interesting open question currently in Leavitt path algebras. If you look at this specific graph, it's not hard to show that the V monoid of this graph is just C sub 2. In other words, 0 and x, where x plus x equals x. Okay, well, that's exactly the same as the V monoid of the standard Leavitt algebra L12. The question is the Leavitt path algebra corresponding to F exactly L12 or not? Okay, and for those of you that were playing around with this example, okay, here's another situation where this question comes up. Is it the case that the Leavitt path algebra of this graph looks like L14? And the answer is, it turns out that this one we know is, but the other ones we don't. Okay, and I think that I will stop there. Are there any questions?
Well, thank you very, very much, Professor Abrams, for a very interesting and fascinating talk, actually. So perhaps I should, maybe we should stop the screen sharing for a minute so that we can see more people, if that's, and okay. I'd like to open the floor to questions, if anybody has questions. Okay, well, I have a couple. If there's no, if there's nobody else asking questions at this point, I was trying to sort of understand some of what you were saying. At one point, I think you were taking a directed graph, and when you're building these weighted algebras. You're taking a directed graph and removing vertices of out degree 1, I think, sort of unnecessary vertices, and then building algebras associated with the corresponding weighted graphs. Are those algebras I guess they're Bergman algebras. Are they Morita equivalent? Do you know
What-
the resulting
so-
algebras?
Right. So the question is, let me make sure I understand the question. So if you remove these vertices that have out degree 1 and
Yeah.
then sort of reconstruct the graph, indeed they'll be Morita equivalent as algebras. Right. So if you form the weighted Leavitt path algebra of the original one, and then you form the weighted Leavitt path algebra of this new one that you get by eliminating the vertices having out degree 1. I mean, you have to eliminate them in a sort of reasonable process. For instance, if you have an out degree 1 vertex here, but you have some vertices coming in, I'm sorry, some edges coming in, if you're going to eliminate this guy, you have to hook these edges to the vertex that had been the range of, but if you do that, then you get the Morita equivalence of the corresponding graphs.
Okay. All right. So there was another little comment that I had. There's some papers recently by people like Arvin Iyer and Ben Steinberg and so on, dealing with non-commutative Sandpile models. I don't know if you've come across these or whether they have any bearing on the kind of questions that you're interested in. So the monoid that comes up is not commutative, and it's minimal ideal is a non-abelian group, apparently. So maybe I don't know whether this gives it sort of a further generalization of the, and there's a lot of natural examples of this, and it sort of relates to random walks on monoids and, you know, Markov chains and so on. So it's a kind of an interesting literature. Do you know anything about that, or whether it's?
No, I know the existence of this literature, but I have not decided whether or not that's going to somehow relate directly here. I mean, certainly in answering this specific type of question that we're looking at, it will not, because the V monoids of an algebra have to be commutative, but maybe there's some appropriate generalization of the V monoid that might be of interest to you.
Are there some other questions that anybody has? It seems not. So let's join in thanking Professor Abrams again for his very fine talk. Thank you.
I would say if someone has questions that come up afterwards, please feel free to email me or contact the organizers, and they can get in touch with me. I'd be happy to answer any questions or field any comments you might have. So thank you very much. Enjoy the rest of your evening.
Thank you, Professor John Milligan.
You're welcome.
By this, we come